Good afternoon. This is Engineer Lee Jareda. I'm here to introduce you to the computer science syllabus for Cambridge IGCSE. I will introduce a simple, interesting part of Chapter 1. Chapter 1 talks about the numbering system. Let's start by what does mean numbering system. Numbering system is simply the number we learned when we were 5 and 6 years old. Our numbering system we learned is the decimal. We all know our decimal system, right? Our decimal system is start from 0 to 9, if you remember. And it is, this is the one with the green on the left. And it is repeated. We call those units, which is from 0 to 9, tenth, hundredth, and thousandth. This is our system, okay? Let's remember what we learned in year 2 and 3 and 4, where we were placing our numbers. If we start by a simple number like 29, 29 is 2 tenths and 1 and 9 units, right? I think you know this. Let's go to a greater number, 587. From what we said, it's 5 of the 100, 8 of the tens, and 7 from the unit. This is a simple, quick revision for our numbering system we learned in math in our early years. Let's go to a bigger number, 6398, which is 6,000. So it's 1,390, 9 tenths, and 8. I know that you know all this since your early years, but this is a quick revision for it. The only new thing we will know about this here is that this decimal system in computer system terminology, we call it denary system. But it is the decimal system. Simply, it is the decimal system. Okay. Let's go to a new concept introduced by the computer science. Any computer or any microprocessor device works only with electricity. Electricity or electric signal is through tiny lamps. These lamps, to admit the flow of electricity, is either on or off. On or off. On, as we always say, it's a 1, and off, as we always say, it's a 0. Okay? So when you switch on and off your computer or your lamp or your electric flow, it is either on, which is a 1, or off, which is a 0. Okay. So basically, the computer does not understand anything except an on or an off. And this is a 2-number system, and 2-number system is a binary system. By coming from by, 2. Okay? The same concept of our denary or decimal system, when my base is 10, so the units is 10 to the power 0, the tens 10 to the power 1, 10 to the power 2, 10 to the power 3. is 1, 10, 100,000. Let's do it in our binary system. 10 to the power 0 is 1. Okay? We have to always remember that anything to the power 0 is 1. 1,000 to the power 0 is 1. Don't get confused. 2 to the power 1 is 2. 2 to the power 2 is 4. 2 to the power 3 is 8. 16, 32, 64, and finally 128. Sorry. Why do I say finally? Because we are used to the concept of 8 bits. You will tell me this is 7, yes, but I started by a 0. So it's 1, 2, 3, 4, 5, 6, 7, 8. This small element is called a bit. Okay? This bit is simply the lamp that is switched on or off. Okay? What are those numbers? Those are the denary of the base 2 system, of the binary system. We will learn a simple transformation from binary to denary and denary to binary. Okay? I will take these numbers. I will not go very far. Let's start by this 29. How do I transform the 29 into a binary value? 29 in denary. I will make it a figure in binary. Okay. 29. How do I do it? It's a very simple, straightforward way. Any value that is greater than the 29 is a 0. So, or we can say it, does the 29 contain the 128? The answer is no. Does the 29 contain 64? It's another no. Does the 29 contain the 32? Again, it's a no. Okay. Now we have to get it. Does the 29 contain the 16? The answer is yes. So it's a 1. So 29 minus 16, the remainder is 13. I have a 13 with me. Okay. Does the 13 contain an 8? The answer is yes. So it's okay. I have a 1. With a remainder of 5, 13 minus 8 is a 5. So I will go to, does the 5 contain a 4? Yes. With a remainder of 1. Does the 1 contain a 2? The answer is no again. But does the 1 contains a 1? The answer is yes. So the 29 in binary is simply 000 11101. This is how the computer will understand the 29. It will be a 9 position of 9 lamp, or 8 position of 8 lamp, which we call them 8 bit. Okay, let's do another one. Let's go a little bit bigger. 54. Yalla. Does the 54 contains a 128? It's a no. 64, no. 32, yes. Sorry. Yes. So I consumed a 32. Remainder is 54 minus 32 is 22. Is it 22? Does the 22 contain the 16? The answer is yes. Does the 22 contain the 16, the answer is yes, and remainder is 6. 22 minus 16 is 6. Does the 6 contains an 8? Oh, I don't know. No. Let's make those a little bit bold to be clear and bigger. Does the 6 contains an 8? It's a no. But does the 6 contains a 4? Yes, and remainder 2. Does the 2 contains a 2? It's a yes, and remainder is 0. It does not contain a 1. So again, the 54 in binary is 0, 0, sorry, 0, 0, 1, 1, 0, 1, 1, 0. So how do we transfer a decimal, or in computer science we call it denary, number to a binary number? Is as simple as that. With this simple table, I distribute my denary number on the different values here. As simple as whenever the number I have contains the number I pass by in order from left to right, it's a 1. If it is greater, it's a 0. And when I find a 1, I leave it and I take the remainder and resume. Okay? Let's make another one, and this is the final one. Let's do a 79, bigger. What does the 79 do? Does it have 128? The answer is no. Does it have a 64? The answer is yes. Okay, so 79 minus 64 is a 1, and the remainder is, let's see, here is the last one. 79 minus 64 is 15. Does it have a 32? No. Does it have a 16? No. Does it have an 8? Yes. And the remainder is 7. Does the 7 has a 4? Yes. Remainder is 3. Does the 3 has a 2? Yes. And remainder is 1 again. So the 79 is 0, 1, 0, 0, 1, 2, 3, 4, 4 ones. I wish it's clear till here. So this is the very simple way of transforming a decimal or denary number to a binary number, which is only represented by a 0 or a 1 by enough and a none of the bit, which is the tiniest lamp used in the electric signal in the computer. Another thing I would love to tell you that, as we said, we use always an 8-bit register, and 8-bit are known as a byte. This is the smallest unit. The tiniest unit is a bit, but the smallest unit used in the computer is called byte. Okay, let's do the opposite. Let's start by this binary number, and transform it into a digital. 1 second to make a separation here. We'll start by the binary number, which is 1, 0, 0, 1, 0, 0, 1. What do you think? So what we will do, we'll do this. We will distribute the figure as it is: 1, 0, 0, 1, 0, 0, 1, and we forgot a number, so this is a 0, because those are only 7 numbers. Okay. So what is the analog denary number? It is the multiplication of these values by these coefficients. So 1 times 128 is 128. So it's 128 plus 0 times 64 is 0. 0 times 32 is 0. So I will not consider the 0. But I have 1 times 16 is 16. So I will add it. 0 times 8 is 0. 0 times 4 is 0. 1 times 2 is 2. So I will consider it. And 0 times 1 is 0. So the analog denary number for this binary number is 146. So this is the vice versa. I am transforming from binary to denary. Another one, let's do it. It is again, we go from left to right, 0, 0, 1, 1, 0, 0, 1, 1. Okay. Let's go. The 128 has a 0, so I don't care. 64 has a 0, I don't care. But the 32 has a 1, so 32 plus 1 times 1 is 32. The 16 times 1 is 16. The 8, I don't care. The 4, I don't care. The 2 is yes, it has a 1. And the 1 has a 1. So this value is 51 in denary. I wish that it is clear till now. Let's go now and make some practice from the past paper of the IGCSE and see how it is interesting and so easy. We are going to solve some questions from the IGCSE past paper from this chapter, chapter 1, the numbering system, about the binary and denary. For your info, what we talked about is about 30% of the chapter. So we covered 30% of the first chapter out of 6 theory chapters. And again, I want to clarify that the computer science is a short subject. Okay, let's go. An alarm clock is controlled by a microprocessor. Microprocessor is the simplest style of computer. We don't define it as computer. We will go in deep with this in chapter 3 in the theory syllabus, and then, but we say that the microprocessor also works with the binary as it is based on electric signals. It uses a 24-hour clock. The hour is represented by an 8-bit register, A, and the number of minutes is represented by another 8-bit register, B. Identify what time is represented by the following 2 8-bit registers. As simple as we will neglect all the zeros because 0 times anything is 0. Then we will respect the ones. So here I have a 16 and a 2. So it is an 18. So I am in 18 hours. What about the minutes? It is 32 plus 16 plus 4 plus 1. So it's 21 plus 32. It is 53. So the timing is, as simple as 18 hours, 53 minutes. And we took the 2 points. Now he's asking me about the opposite. An alarm has been set for 7:30. 2 8-bit registers, C and D, are used to represent the hours and minutes. Show how 730 would be represented by these two registers. So he wants to see these binary now. The first one is for the 7, second one is for the 30. So is the 7, does the 7 contains 128? No. Let's make it a little bit. Okay. 64, no. 32, no. 16, no. 8, no. 4, yes. The 7 has a 4. Remainder 3. The 3 has a 2, yes. And remainder 1. The 1 has a 1, yes. So this is the 7. Now we'll have the 30. Let's write it a little bit up in order that we can see. 64, 32, 16, 8, 4, 2, and 1. Okay. Does the 30 has 128? The answer is no. 64, no. 32, no. But the 30 contains a 16, yes. Remainder 14. The 14 contains an 8, yes. Remainder 6. The 6 contains 4, yes. Remainder 2. The 2 contains a 2, yes. Remainder 0, so I don't have a 1 here. Easy. So like this, I got the 4 marks of the question. It is that easy. Okay, let's go to another one before we leave. Let's go to one of the latest. As we can see that this question is October, November 2020. So it's one of the latest here. Okay. 4 denary to 8-bit binary conversion are given. Take to show if each denary to 8-bit binary conversion is correct or incorrect. This is a very interesting one. You can start by the binary and converting it to denary, or the denary to convert it to binary. Okay, I still have my famous arrangement. I don't want you to ever forget that those are 2 to the power 0, 2 to the power 1, 2 to the power 2, until 2 to the power 7. And these are 8 bits, which are 1 byte. Don't forget this. Tab, okay. So it is, the first one is 1, 0, 0, 1, 0, 0, 0, 1. Okay. Let's see, it is 128. We can say it is 128 plus 16 plus 1, which is 128 plus 17 is 128 plus 17, 145. I want to remind you that we are not allowed calculator, so we have our time. So 126 plus 16 plus 1 is 145, so this is correct. This is correct. Okay. Let's go to this. Let's make it the same way. 1, 0, 1, 1, 0, 1, 0, 1. It is 128 plus 32 plus 16 plus 4 plus 1. We have to take our time to make it because again, we're not allowed calculator. Again, it's 128 plus 32 is 160, plus 16 is 176, plus 4 is 180, plus 1 is 181. So it's not 179. So unfortunately, this is not correct. This is incorrect. The 11. 11 could not be easier. As simple as I will neglect all the ones before. Let's make it the other way. Does the 11 contain the 128? No. 64, no. 32, no. 16, no. 8, yes, the 11 contains an 8. Contains and the remainder is 3. 3 has the 4, no. Has the 2, yes. Remainder 1 and 1. So it doesn't look correct. So again, it is incorrect. Let's go to the 100. Does the 100 contains 128? The answer is no. But does it contain 64? Yes. So it's a 1, and remainder is 100 minus 64 is 36, or what? Yes, it is 36. The 36 has a 32? Yes. Remainder 4. Does the 4 has a 16? No. Does the 4 has an 8? No. Does the 4 has a 4? Yes. And nothing. No remainder. So it is 0, 1, 1. 3 zeros, 1, 0. No, it's 0, 0, 1, 0, 0. So it's again incorrect. So we solve it both ways. Once starting by the binary and converting it to denary and make sure that it's right or wrong. And the last two, we started by the denary and we distributed them on our arrangement of bits. And we found that they are incorrect, unfortunately. So again, this is the way the question comes. If you look to question B, that we will not solve because it converts the 12-bit binary into hexadecimal. Hexadecimal is another numbering system with a base of 16. Don't get scared, it's an easy system as well. They started to invent the hexadecimal system when the memory became huge. When you can see the bits, the minimal bit flowing everywhere. So they started to use the hexadecimal system based on 16, which we will talk about in our next lesson. So the next part of this lesson, of this chapter, is the permutation between binary and denary to binary that we already covered, and then we will introduce the hexa that so we'll permute between the three of them. It is as easy as this one, and this is one of the most interesting chapters, and you're not allowed to miss a point in it. Yalla, good luck, and see you in our next class, inshallah. Bye-bye.